next, let's discuss seasonal time series. Seasonal time series means time series with periodic patterns, and it is useful in predicting quarterly earnings because they have patterns and pricing weather related derivative, analysis of transaction data like high frequency data, for example, U-shaped pattern in the intraday trading, intensity, volatility, etc. So it is U-shaped because in the intraday trading, when market opens, when market closes, they have most trading volumes, most liquidity. That's why it is U-shaped. Example 1. Monthly US housing starts from January 1952 to January 26. The data are in the Sound unit. See figure 1 and compute the sample autocorrelation function of series and its different data. Okay, so let's take a look at the figure 1. Yes, this is the figure. Time plot of monthly US housing starts 1952, January 2012, February. So clearly there is up and down. Clearly there is a pattern. There is seasonality. Pattern called seasonality. Example 2. Quarterly earnings of Johnson and Johnson. See the plot figure 2 and 3 and the sample autocorrelation function. And yeah, figure 2 time plot of quarterly earning of Johnson and Johnson. Okay, it's a quarterly earning. It seems that it is upward, it is upward, but there is also up and down seasonality. Okay, and then it's a time plot of quarter log earning. So yeah, it is exponential. So to linearize it, we can take a log. So in the logged earning of Johnson and Johnson, we can see uh, this seasonality pattern. Earning per share of Coca-Cola. Okay, time plot of quarterly earning per share of Coca-Cola, and then yeah, this one. Yes, example 3, quarterly earning per share of Coca-Cola from 1983 to 2009. Now multiplicative model. Consider housing start series. Let YT be the monthly data, denoting 1959 as year 0. We can write the time index as t equal year plus month. For example, y1 is y01, y2, y02, y14. Y14 is y12, etc. Something like that. Okay. The multiplicative model is based on the following consideration. Yeah, following consideration, something like this. So, yeah, we have a month. So, in order to model monthly seasonality, we have a month and we have a year. So, well, there is a pattern across year and then pattern across January. If we use only annual data for example, with every January, then we don't have a seasonality. If we use every March data, then we don't have seasonality. However, if we use entire data, monthly data for each year, then we should take into account both yearly trend and monthly seasonality. Here the column dependency is the usually leg minus 1, leg minus 2 dependency. So in column, yeah, something like that. That is monthly dependence. So January is affected by February is affected by January, March is affected by February, November is affected by October, and December is affected by November. So it's a T minus 1 lag. Okay. However, there is also yearly dependency. We call so for leg 1, leg minus 2 dependency, this is monthly dependence. We call them the regular dependence. The low dependency, now dependence across log, this one and this one. Now, this possibly depends on, okay, this possibly depends on this, right? So to relative the year to year dependence, we call them the seasonal dependence. The multiplicative model says that the regular and seasonal dependence are orthogonal to each other. So, well, the monthly dependent, the dependency between this and this possibly they're orthogonal. They don't interact. That is multiplicative model. Okay. Now for the airline model for quarterly series, so airline model is famous. RT minus one. Okay, the quarterly dependence, and then RT minus one minus RT minus four quarterly dependence, and T minus five. Okay, for quarterly series. So it models the like monthly dependence, and then monthly dependence is again depends on quarterly. All right. So we model this one as AT minus Sarah 1 AT minus 4 Sarah 4 AT minus 4 Sarah 1 4 AT minus 5, or well, if we use uh, back shift operator, back operator, then 1 minus b 1 minus b 4 RT, and 1 minus 1 b 1 minus 4 b 4 AT. Now we define the different series of WT as WT is RT minus RT minus 1 minus RT minus 4 plus RT minus 5, which is the difference in difference. RT minus RT minus 1 minus RT minus 4 minus RT minus 5. So it is called regular and seasonal difference model. We have a regular difference here, and then between the parentheses we have a seasonal differences series. Okay. Now autocorrelation function W has the nice symmetric structure. So S minus 1, S plus 1 is rho 1, rho S. Also rho L is equal for L is greater than S plus 1. We can easily check it. This model is widely applicable to many seasonal time series. Also, multiplicative model means that the regular and the seasonal dependencies are roughly orthogonal to each other. Now, forecast exhibits the same pattern as the observed series. See figure 5. Okay, figure 5. So, yeah, here, well, we can forecast the future. Okay, we can forecast the future over here. Okay, at the end, future. So, we make a forecast based on trend, yearly trend, and quarterly up and down movement, right? So we use both information. Exponential smoothing method by taking log. Okay. Example detailed analysis J&J earning and our demonstration is here. So yeah, you can run this one. Okay, this is available in our yeah folder. So this code is available, right? This is seasonal time series over here. Okay, so we have data, and then we have code over here, so we can run it. Okay, so let's skip. For monthly data, the airline model becomes now 1 minus b is different than 1 minus b 12 RT. Okay, which is 1 minus theta 1b, 1 minus theta 12b 12 AT. Okay, for this one, the pattern of autocorrelation function, yeah, we can do something similar to this one. Okay, you can easily check it. And then yeah, let's skip. Now remark parameterization in R with additional exponential variable x in Riemann model. Now in R is, if we use Python is different, but when we use R is a bit special. Okay, when we model Riemann, R is special, so R use model something like this. So WT is phi 1 WT minus 1 plus and phi P WT minus P and AT theta 1 AT minus 1, something like that. Where now WT is YT minus beta 0 minus beta XT. Okay, something like this. This is the way R model time series. Okay, this is the proper way to handle regression model with time series error, because WT minus not subject the effect of XT minus 1. So we regard the entire this set as one variable. Okay, So it is different from the basically this model. Okay, so if we can expand it and we can write it, but the estimation is kind of different. 40y t minus contains the effects of x t minus 1. Okay, now long memory warning, meaning autocorrelation function decays to zero very slowly, which means that we have correlation over long horizon. History affects friends a lot. Okay, history doesn't die out quickly. Example, autocorrelation function of squared or absolutely done. Okay, HF file small but decay very slowly. That's the pattern of squared, the volatility process. Then how to model long memory? Then we use a fractional difference model, namely 1 minus b drt, where d is between minus 0.5 and 0.5. Important in theory, yes. In practice, it is not so sure. Okay, not so sure. But we have good package to estimate even this process. In R, the package RUGARCH may be used to estimate the fractionally integrated ARIMA model. Yeah, it is called this fractional, right? This fractionally integrated ARIMA model, ARMA model. The package can also used for GARCH modeling. Now, summary of paper. By checking sample autocorrelation function, we can find moving average order. By checking sample partial autocorrelation function, we can check AR autocorrelation order, ARO order. Some package has automatic procedure to select the simple method for conditional mean of financial term series. For example, R use AR for AR model. We can also check a fitted model before forecasting, like a residual of autocorrelation function and the heteroscedasticity, in order to check whether residuals error term after we estimate a model has any pattern. If it has pattern, we didn't model properly. Didn't model sufficiently. Interpretation of a model, for example, constant term and for an AR1 with coefficient phi 1, the speed of mean reverting as measured by half-life is k equal log 0.5 divided log absolute value of phi 1. Okay. For MAQ model, forecast delivers the mean in Q plus 1 step. Okay. Make proper use of regression model with time series error. Like, for example, regression error on residual. Perform joint estimation instead of using any two-step procedure like Cochrane-Urquhart procedure. Now, basic properties of random walk model and multiplicity seasonal model, especially the so-called airline model.